Good morning, Calculus Day 2. I'm Gary Parker. For those of you who haven't met me yet, but most of you have, we are missing one person. Hopefully we will find him soon. So let's take a look at our online stuff. All right, so just a reminder here on the course homepage, a link to the whole textbook where you can grab a PDF if you want. Solutions manual, daily work schedule. We started looking at the previous first section of Calculus 1 from the old version of the book, and now we're going to transition into the new one. Hopefully you did that intro to how to type things into this computer homework system and maybe started the 2.0 homework. So we're going to work on that and 2.1 today. And remember, each section is set up pretty similar. There's a link to the online textbook with the main ideas that we're going to do there. And then some videos I've put together from me and other people, and then the homework. So you get a whole bunch of resources, including me in class here. All right. Whiteboard time. So we were playing around with the idea of what is calculus, and we're going to continue that today. And I said the other day that calculus is a study of infinity. There's many studies of infinity. And we looked at a couple of examples of what infinity means, which is many, many things in the world of mathematics. And the two main problems that we're going to be studying this year, which are the rate of change problem. And rate of change is synonymous with slope. So just a reminder, often when we find slope, we need 2 points and we find the difference in the y values. And we divide by the difference in the x values. And these changes in the top, right? So this is a change in y here. And down below, we have a change in x. And I mentioned yesterday in class that change has a symbol in mathematics, and it's often this triangle right here, which is the Greek capital delta. So delta y is how I would say that. One way to say it, because that is the delta symbol, which really means change in y. So when I see that, I could say delta y, but change in y would be a better way to read that. And then down below, we have a change in x. And often, y is a function of x. And so any change in x is going to produce a change in y because x is our input and y is our output, right? So other things about the change in x, that's also a change in input. And that input is also referred to as our independent variable because it can do whatever it wants, sort of. And the y is the corresponding output variable. And because of this functional relationship here, y depends on x, right? That's what this means. So this is our dependent variable. So we have a change in the dependent variable. And this is the main study for this quarter. So this is Calculus 1. This idea is called differential calculus, and that's Calc 1. So Calculus 1 is this study right here. It is called differential calculus. And it goes hand in hand with kind of a reverse idea, which is Calc 2, integral calculus. So just a quick note, we looked at yesterday, we'll look at least one more example today called integral calculus. And integral calculus looks at a couple of things. It looks at accumulation of values. example of. And that accumulation of values can be graphically looked at as area. That area is usually under some function. And so we looked at the other day a graph of velocity function, and then we looked at the area under that graph of velocity function. That gave us a position function. If we looked at a position function and we looked at the rate of change of the position function, that gave us a velocity function. So we can go back and forth between these two. And Calculus 2 focuses more on that accumulation, the area, and the back and forth between them. So right now we're just going to mainly focus on these rates of change. To do these rates of change, however, the slope gets a little bit complicated because we are looking for a rate of change not between 2 points but at a point. Okay, so we have to find this interesting idea of slope at a point, which is kind of weird. It's a conundrum. Because normally to find a slope, we need 2 points. And if those 2 points are merged into one, then the denominator turns to a 0, and we can't divide by 0. And we'll see that in just a moment. All right, so I've got some things for you guys to play with after I do an example. Let's show the desktop for a second to get a preview. Desmos is an online graphing calculator. There's another online graphing calculator called GeoGebra, and it's been around a little longer than Desmos. Desmos in some ways is trying to be like GeoGebra, and now they're in competition. So I set up a couple of files that we're going to play with here, where I have this graph of a parabola and 2 points on the parabola, and then I'm having the computer find the slope between those 2 points. So I'm going to do a manual version of this, and I have another version of that, and I'm going to share these with you for you to play with. And these points can be grabbed and moved around. And the point is fixed on the parabola here as I move it around. And this one, again, pretty similar. I got a couple of points that I can play with here. So I'll let you play in just a moment. So let's play more with the idea of slope. And we're going to look at slope on a parabola. And so let's, on a piece of paper, hopefully you're playing along with me with some paper here. Graph paper is very nice for a class like this. We're going to take a look at the function y equals x squared. And I'm using the function notation just to emphasize it's a function. It has an input and an output. Input is x, output is the square of x. Okay? And so let's just kind of zoom in near the origin here. And plot a couple of points. So we know that if we square 0, we get 0, so we have a point at the origin. If we square 1, we get 1. If we square 2, we get 4. If we square 3, we're kind of off my grid here, so I'm not going to worry about that one right there. If I squared 1/2, I would get 1/4 down there. And on the other side, if we did some more like -1 over here, the square of -1 is +1. Square of -1/2 is +1/4. So this graph here is this U-shaped thing. It's curved at the bottom, and then it rises up, and there's the graph to the best of my artistic ability this morning. So where's that other point? Over here-ish. Whoa, I missed. Again, go this way. Oh man, what's wrong with my whiteboard or my hand? Something's wrong. Oh well. Some days I'm good with this virtual whiteboard, other days it is a challenge. So if I wanted to find a slope on this, I could select 2 points, like say the point 1, 1 and the point 2, 4, and I could find the slope between them. And that means I'm oops, choose a different color. Choose, how about black? So from this point to that point right there, imagine a straight line going through them, and I want to find that slope, that rise to get up here, and then the run to get over. And so we can see pretty clearly that to get from 1 to 4, we have a rise of 3, and to get from 1 to 2 for x, we have a run of 1. So between those 2 points there, we have a slope of 3. Look at this in tabular form, x and y. We get the point 0, 0, 1, 1, 2, 4, and we just found our rise, 3, and our run, 1. And so that's this slope right there. Now, if you imagine, like if we zoomed in on that curve a bit, it looks more like this. If we zoom in, when you're walking at the bottom here, it's not very steep, it's pretty shallow, but then as I move over and I start walking up here, well, then it's a bit steeper, right? And up here, right, I'm scrambling and reaching and trying to climb up there. So it's much steeper over here than it is down here, right? Shallow. And every tiny movement I make, say in this direction right here, it's going to keep getting steeper. So if instead of looking from, say, x equals 1 to x equals 2, if I only went over to maybe x equals 1.5, I would have a slightly different slope. So if I went from 1 to 1.5, would it be steeper or shallower than the slope between 1 and 2? We want to chime in here and help me out. Let's get chat back up. Shallower, says Evan, and I agree. So I'm just going to throw in another point here. So I'm sneaking in the point 1.5 for x, and if I take 1.5 times 1.5, I'm pretty sure I get 2.25. And so the slope between these 2 points is a little bit different. My rise is going to be 1.25, and my run is going to be 0.5, which altogether I think gives me a slope of 2.5. So we might want to double check that on a calculator, but it is, right, not as steep as the 3, because I'm only going up to from, let's see, here to there. The graph's a little bit off. That point should be more like right there. So this slope is a little bit shallower than that slope over there. So there m is about 2.5. And if I got closer still to 1, we want to figure out what's going to happen. So this is where I'm going to let you guys play a little bit. So the idea of we're trying to get to is we can easily find the slope of between 2 points. So this is easy, right? Slope between 2 points. What's not so easy, call this one hard, is the idea of slope at a point. So like over here, let's erase that version of Gary for a second. Goodbye, Gary. And let's say Gary is standing at this point right there, and he's balancing on a toe there. So my other leg is out in the air. Maybe I'm doing a tree pose here. Here's Gary balancing on that single point right there. What is the slope at that single point? Okay. That's what we're going to try and estimate, guess, figure out, and then we'll look more at how calculus is going to give us some tools to more definitively find that. Okay, so to do that, I am going to make a couple of breakout rooms. And let's do 2 rooms. And let's see, what do we get? We get Abigail and Kelsey versus Evan and Cole today. So that's kind of a random assortment collection of you guys. And then in just a minute, I'll open those rooms. In the meantime, I am going to chat you guys the links to these apps I have here. So share. Give me the link, please. There you are. Okay, so this is going to be group 1, Abigail and Kelsey. well today. And there is your link. And then we've got Evan and Cole. You're going to jump into this slightly different one, and the link is coming. Okay, so there's the other link for Evan and Cole there. So if you could click on your respective links to load these pages here. And let's see, I'm trying to remember what those look like when you view them. How is it different from what I see? So an incognito window to double check. So you should end up with your own copy of this thing, and you can mess around with it and it shouldn't affect mine. So then you should be able to move a point or two. And hopefully it's not very big. Interesting. It might depend on the browser that you look at. So I was in Google Chrome there. I wonder what it looks like in Firefox. Do I have Firefox? If you have a different browser than either of these, it's one thing about the internet. It doesn't behave on every browser. Please. Looks a little different on each browser if it's a complicated tool. So hopefully you can find a full screen version of this. I found like if you're on a tablet, GeoGebra is a little touchy on a tablet when you try to point and click on the screen to grab stuff. It works better with a mouse than a finger. All right, so you guys have those. I'll explain what you're gonna do with them. And so you're gonna go into the breakout room and talk to your partner. So hopefully you have a microphone that works, otherwise you'll have to chat to each other. Let's see, in the first room here, that, and to see my calculator stuff. All right, so I have 2 points, and the 2 points are movable, and as you move them, the slope will adjust. So what I want you to do, I want you to play around with these 2 points here and see if you can estimate what is the slope when x equals 1. So that's the Kelsey and Abigail question. What is the slope when x equals 1? And so you want to move these points around and come up with your best estimate for that. And then the app that Evan and Cole have is pretty similar. You can move these points around, and you guys, I want to have you estimate what is the slope when x equals 2. So that would be around the point 2, 4. So good luck. I'm going to give you just a few minutes to work on this. You should get a message saying your breakout room is open. Go ahead, click and join.
Sir, you're
Mr.
muted.
Parker, I think you're muted.
Yeah, you're muted.
Oh, darn. Am I unmuted?
Yeah.
Yes.
Oh, good. Okay. Sorry about that. When you come back from a breakout room, it automatically mutes sometimes, most of the time. Anyway, okay, so here we go. I have, I tried to draw my best slope line here at the point 1, 1, and then I tried to repeat drawing my slope line at the point 2, 4 here, and I want to estimate what those slopes are. And I gave you this graphical version, graphing calculator version to kind of play around with that. So there's a couple of ways I could approach it. So if I was looking at the point 2, 4, I could just place my points pretty close together by 2, 4. Oops, come on. And as I move them closer together, I can see that the slope is approaching 4, is what it looks like. And if I go try to get right on there, put the points on top of each other, it doesn't quite let that happen. But it's a little above 4 over there. It's a little below 4 over there. 4 is in the middle, so 4 seems like you know, a pretty good guess. Other one works the same way. I could approach it a little bit differently by putting one of the points exactly on 1, 1, and then moving the other point toward it. So the points could be on each side of the target point, approaching each other, or they could have, you could have one point stay still and the other point approach it. But if I do get the points right on top of each other, notice the slope vanishes because we try to divide by 0, which is a problem, mathematically speaking. So the next thing I want to do is take a look at this a little more systematically in a table. So let's pick on x equals 1 in this table, and we want to estimate slope by that point. Oops. Estimate slope. And so we have our x values and our y values are x squared. So at 1, we get 1. And if I go all the way over to 2, and let's make another column for slope here. And that's the slope from the point 1, 1. So the slope from 1, 1, oops, that's not 2, 2, it should be 2, 4. Is I have a rise of 3 and a run of 1, so I get a slope of 3 there. And I want to get closer to 1, so maybe I'll look at 1.5 next. If I square 1.5, I get 2.5. And so then over here, I get a difference of 1.5 in the top divided by 0.5 in the bottom. Oops, something's not right there. It should be 2.25. So 1.25 divided by 0.5, and I'm going to get a slope of 2.5 there. And I can just keep getting closer to 1, so maybe I might try 1.1 next. So now I need a calculator to help me out with this. And given the repetitive nature of these calculations, a spreadsheet would be a good way to go, so I'll show that later. So let's just go 2 plus 2, bring up the Google calculator. And I want, actually I'm going to type it up here, I want to know what is 1 minus 1.1 divided by 1 squared is 1 minus 1.1 squared. Ooh, I did that backwards. So this one is squared. And so I get a slope of 2.1 in that case. And I should have calculated that value. It's whatever 1.1 squared is, and the slope is 2.1. And so I went from a slope of 3, as I move closer, slope of 2.5, 2.1. I could get even closer by plotting the point 1.01, whatever the square of 1.0 was, and find the slope. So back to my calculator. 1.01 squared, 1 minus 1.01, so right in the parentheses, I have my rise there, divided by the parentheses, my run. Enter, and I get 2.01. Interesting. Got a pattern forming, perhaps? Let's do it one more time just for fun. So 1.001, the y value is the square of that. Let's see what our slope is going to be, and I could kind of guess. I think it might be 2.001. Let's actually calculate it. It's good to guess though, as long as you check. And 2.001 is what I get. So I'm starting to see a pattern here. As my x value here approaches 1, so x approaches 1, it seems that over here, the slope m seems to approach 2. Now, I can't actually get to 2 with my slope formula, because if I start at the point 1, 1, right, then I'm switching to this other point to get the slope. And if I try to plug in 1, 1 again, then my slope formula becomes 1 minus 1 over 1 minus 1, which is 0 divided by 0, which does not exist. However, I definitely have a pattern here that says it looks like the slope is 2 at the point 1, 1. So m does seem to be 2 there. So this idea that we're playing with slope at a point is often called instantaneous rate of change. So that's another name for this. So we have what we calculated right here to the best of our ability is slope at a point, which is a strange idea because slope usually involves 2 points. And that means the same thing as an instantaneous rate of change as opposed to an average rate of change. Instantaneous rate of change. So again, the instantaneous rate of change, I believe, is that 2 right there. Each of these other numbers I have over here for slopes, they're the slope between 2 points. So those guys right there are what I refer to as an average rate of change. Average rate of change. And again, the average rate of change, oops, where's my highlighter? There we go, are each of these values right here. And we are predicting that if we get right on top of 1, which isn't possible in a calculation because we can't divide by 0, it seems that the slope is 2. Now I'm only approaching on the right side here, right? I was always picking an x value bigger. What if we went from the other side? I'm going to whip this out on a spreadsheet to show how a spreadsheet can help make these repeated calculations a little easier. Give me a second to get that